Hello again. This is Math 2134 coming to you from the College DePage, and the title of this lecture is Concavity, Inflection, and the Second Derivative Test. Make sure you're an active learner as you watch this video. By way of introduction, there's a difference between these two curves. This one is rising faster and faster, ever faster, and this one is still increasing, but it's increasing at slower rates. A big difference between the two. And another way to characterize the difference is if I were looking at this one on this side and I were to draw the tangent lines would always be underneath the blue curve. And if I were to draw the tangent lines to each point on the other side, on the other curve rather, the tangent lines would always be above the curve. And so this is our introduction to concavity. So over here the slopes of the tangent lines are increasing. Over here they are decreasing. Over here they are above the line of the function, and here they are below the graph of the function. So we define concavity of a function f then. Let f be differentiable on an interval AB. Then the graph is concave upward if f prime, the derivative, is an increasing function on AB. And the graph is called concave down on AB if, again, the derivative f prime is decreasing on AB. So this one is concave up, this one is concave down. Now this can happen on an interval as well. So on the whole of AB, the tangent lines are always underneath the blue curve. So this graph is concave up on all of AB. Similarly here, on all of AB, the tangent lines are above the curve. So the graph of f here is concave downward on the whole of AB. And since the second derivative measures the rate of change of the first derivative, we can have the following theorem. If f double prime is bigger than 0 for every value x in an interval AB, then the graph of f is concave upward on AB. Similarly, if f double prime, the second derivative, is less than 0 for every value x in AB, then the graph of f is concave downward on AB. Now, a lot of times I will ask you questions, or your book will ask you questions, or my math lab will ask you questions to determine the intervals of concavity of the graph of a function. Here's your approach. Determine the values of x for which f double prime is 0 or where f double prime is not defined. And those are kind of like critical points, but now for the first derivative. And identify the open intervals determined by these numbers. So you're slicing the real number line in half again. And then we determine the sign, SIGN, of f double prime in each of those intervals. And to do this, we pick test points and we compute f double prime of C, where C is a conveniently chosen test number in the interval. If the second derivative at C is bigger than 0, we are concave up on that interval. If the second derivative is less than 0, then the graph is concave downward on that interval. So let's do a problem here. Determine where the graph of y equals f of x, this is a cubic function, and there's a plus 32 going on the other line, is concave up and where it is concave down. So we'll take the two derivatives. When we take the first derivative, we will get this. Make sure you can do these calculations. When we take the second derivative, we will get this. And we factor this because we know we're going to be setting this equal to 0. So, and it's defined everywhere because it's a polynomial. So set that equal to 0, we get that x is equal to 1. So the sign diagram then, we'll draw that. Here's x equal 1, and whenever I pick something like 0 less than 1, I get a negative value. When I pick something bigger than 1, perhaps 2, I get a positive value. So it changes from negative to positive. And in fact, that means we're changing from concave down to concave up. And let's see, they were asking, where is it concave upward? It's concave upward over here from 1 to infinity, and it's concave downward over here from minus infinity up to 1. And here's the graph, and you can see what happens. Now here it is, concave down all the way till 1, and then it changes concavity here, and then it's concave up the rest of the way. Let's look at another example. This is another function we've studied before. Y equals f of x equal x plus 1 over x. And we want to know where is it concave up and where is it concave down. Now we should note at the outset that x equal to 0 is not in the domain of f of x. And in fact, the graph will show that. So that cannot be well, later on we'll say that can't be an inflection point, but anyway, we'll take the first derivative and we'll do it term by term. So the derivative of this is 1, and the derivative of this is minus 1 over x squared. So that is the first derivative. We take yet a second derivative and we get this. And so we get f double prime of x is equal to 2 over x cubed. Minus times a minus was a plus. And so what that means is we'll say, well, is this ever equal to 0? It's never equal to 0. Is it ever not defined? Well, it's not defined at 0, and so that tells us, oh, the concavity might change at 0. We do a sign diagram. Here is 0. We pick values over here and values over here. It changes from negative to positive, and if we look at the graph, it is here, and you can see that it is concave up here, and it is concave down here. So concavity changes at x equal to 0. Now we talked about the concavity changing at certain points, and here's an example where the concavity changes. If you carefully look at this function, you can conclude, oh, it looks like it's concave up here, and then it starts being concave down. So you see it changes from growing faster and faster to growing but slower and slower. In economics or business, this point right here, where the concavity changes, and soon we're going to call it an inflection point, is sometimes called the point of diminishing returns. Okay, here's the definition then. And a point on a graph of a continuous function f where the tangent line exists, and look, we're insisting that the tangent line does exist, so that means we can't have a cusp, and where the concavity changes is called a point of inflection or inflection point. Now this is not an inflection point because even though the concavity changes, there's no tangent line that exists. And if I had a cusp where I was going up to a point, that also concavity changes, could change there, but that's not because it doesn't have a tangent line there. Observe that the graph of a function crosses its tangent line at a point of inflection. And you can see examples where that happens. Now, to find inflection points, then here's your procedure. Compute f double prime. Then we're going to determine places where f double prime is equal to 0 or where f double prime does not exist. Okay, now those are the candidate points. That's what it says over here. Those are candidates. That doesn't mean those are inflection points yet. But then you determine the sign, the SIGN of f double prime to the left and right of each of those critical numbers found here. And if there's a change in the f double prime as we move across it, then c comma f of c is an inflection point for f. Okay, so here's an example, a well-known curve. Find the point of inflection of the function y equals f of x equal x cubed. Here's what the graph looks like. When we take the first derivative, we get 3x squared. When we take the second derivative, we get 6x. Now, this is continuous everywhere, and 0 for x equals 0. That means x equals 0 is a point that we have to test. And so we'll pick something to the left and something to the right and plug it into this second derivative. We get negative values here and positive values here. So it changes concavity. If you chase that all the way back, the point 0, 0 then is an inflection point. And indeed, you can see that it changes from being concave down to being concave up. Here we're to determine the intervals where the graph of y equals f of x equal x minus 1 whole to the 5 over 3 is concave upward and where it's concave downward, and find the inflection points. So we take the first derivative. Please make sure that you're doing these calculations. It is good practice. And then we take the second derivative and can simplify it this way. Now notice this is never equal to 0, but it is not defined when x is equal to 1. So we can make the sign diagram down here, and 1 is the point we need to check. So we pick values less than 1, and we see, oh, f double prime is negative, and greater than 1, we see f double prime is positive. So that means it does change concavity, and that means that is an inflection point. That means it's concave down over here and concave up over here. And so that means the answer is it's concave downward minus infinity to 1 and concave upward on 1 to infinity. Here's another graph. This is similar to a very famous curve. It looks a little bit like a bell-shaped curve. Determine the intervals where the graph of the function y equals f of x equal 1 over x squared plus 1 in the denominator is concave upward, and where is concave downward, and find the inflection points. Okay, we take the first derivative. Now, this is good practice, so the first derivative of this is going to be minus 1, this business, to the minus 2 times 2x. When you simplify it, you get this, and you could write it this way. That minus sign is still there. It's hard to see, but that is negative. So now we're going to take the derivative again, but now we have to do the quotient rule. So, and remember that the minus is still there. So it's going to be denominator times derivative of the numerator. There's where they put the minus sign, minus numerator, and there's where they put the minus again. It's minus a minus numerator times derivative of the denominator. That's 2, this business, to the 1, and the derivative inside by the chain rule is 2x, and this is all over x squared plus 1 whole to the 4th. Now we have to do algebra on this to simplify this in order to answer the question, because we're trying to figure out when this is equal to 0. So we factor out x squared plus 1 and simplify inside, and this is what we get. And when we simplify it again by factoring out the 2 out of here, we have this. Now, we have places where it could be. It's places where this is undefined, and also places where it can be 0. Okay, so we will look at those then. So it can be 0 when x is equal to plus or minus the square root of 3. Now that is when you simplify that, that is either the square root of 3 over 3, or it's minus the square root of 3 over 3. And we're going to test those in the second derivative, and we're using the sign test, and you see that it is positive here. It's negative on both sides of 0, so you see even though 0 was a critical point, it did not change concavity there. It's concave down, and it's positive here. So where does it change? Minus square root of 3 over 3 and plus square root of 3 over 3. They ask us to determine the intervals where this is concave up and concave down, and so we're concave up on minus infinity to minus square root of 3 over 3 and square root of 3 over 3 to infinity, and it's concave down in between the two. And if you look at the picture, you can see that that's exactly the way it is. In example 6, you're to sketch the graph of the function that satisfies all of these properties. And you notice they're saying things about the derivative and the second derivative here, and these are a bunch of ordered pairs. Well, we plot the points that we have for 1, 2, 3, 4, 5. We plot those 5 points, and I plot those 5 points right here. So you can see that I've plotted several of those points. And then it has to be increasing from minus infinity to 1 and from 1 to infinity. Well, from minus infinity to minus 1 it is increasing, and from 1 to infinity it is increasing. So that works. I know that because that's what a derivative means. And it is decreasing in between, and the function is decreasing in between. So that's all good. It has to be concave down up to 0, and you see we do this and we get concave down to 0, and as we go the other way, it is concave up. Now they said graph the graph of a function. It didn't have to be exactly this function, but that's a very simple function to have graphed to satisfy this. If I ask you a question like this, I have to carefully look to see, did you satisfy all these conditions? I have asked problems like this before. Life is a word problem, so we do word problems. So we're talking about what is the effect of advertising on sales. So here is a formula, and the amount of money is in thousands of dollars. that they spend on advertising, and this is the sales as a function of how much they spend on advertising. And so you have this, and we take the first derivative and the second derivative. We're trying to find the inflection point. The first derivative and the second derivative, and then we'll set the second derivative rather equal to 0, and we find out that this is equal to 0. So happens when x is equal to 50. The reason you get that number is because you have 0.06 there. And so it's bigger than 0 when x is less than 50, and it's less than 0 when x is greater than 50. So that means that it changes from being concave up to concave down. That is a point of diminishing returns. And here's example 8. It's a similar kind of thing. It's talking about the consumer price index. And so it is I of t is equal to this, 0 less than or equal to t, and t equals 0 corresponds to the beginning of 2003. Find the point of inflection and discuss its significance. So we're going to take the first derivative, getting this, the second derivative, getting this, and we know we're going to plug that in and set it equal to 0. That's why we factored it. We find that it's bigger than 0 when t is less than 5, and it's less than 0 when t is 5. So that means this point is where it changes from being increasing, ever increasing faster and faster, to still increasing but increasing slower. Okay, and the answer to this is it actually began in 2008. Now this is dealing really with consumer price index, and so I could be index or I could be inflation, and so you see inflation is slowing down now, so that is relief is beginning. And it's 2008 because t equals 0 was 2003. This brings us to the concept of the second derivative test. If we look at this situation where there is a relative maximum at x equals c, you see that, well, the first derivative is equal to 0, but the second derivative, this is concave down. So relative max, concave down. Here we have a relative min. The first derivative was equal to 0, but the second derivative was positive, and so it is concave up and relative min. This is the second derivative test. So here is how you perform a second derivative test. You compute the first and second derivatives. We do that quite a bit. And then we find the critical numbers of f for which f prime of x is equal to 0. So we are looking at places where f prime of x equals 0. Those are critical numbers like we talked about before. Then we're going to compute f double prime at each of those points. So if the second derivative is less than 0, concave down, it's a relative max. If it is greater than 0, it's a relative min. And if it's equal to 0, or if the second derivative doesn't exist, the test fails. That is, it's inconclusive. And it really fails in a very strong way. Here I've got the red function, and when I take the derivative of the red function, I will get the green function, and you see it's 0 there, even though the red function has a minimum at x equals 0. The blue is kind of the negative of that, but you see it has a maximum, so it could be a max, could be a min, and I didn't show you this, but it also could be none of the above. So the second derivative test does not yield a conclusion if f double prime is equal to 0, or f double prime doesn't exist. So this test fails, unlike the first derivative test. Let's use this to determine the relative extrema of this function using the second derivative test. And by the way, this is a function that we have actually studied before in a previous lecture. We take the first derivative and we get this. And we know we need to find the critical points, so we're going to factor this. So we set it equals 0, and we'll find that x equal minus 2 and x equal 4 are the critical points. Now we take the second derivative, so we take the derivative yet again of this, and I factor it because I want to be able to compute it easily. And I will say what happens when we have minus 2 and what happens when we have 4. When I get minus 2, I find that this is minus 18, it is negative, and at 4, it is 18 and it is positive. So the second derivative test tells us that f of minus 2 equals 60 is a relative maximum, and it tells us that 4 minus 48 is a relative minimum. Now, to compare the first derivative test just a little bit, first derivative test always works. It's a lot of work, but it always works. The second derivative test can fail and fail spectacularly. You are supposed to know both of these tests. And here's a nice little summary chart about the signs of f prime and f double prime. You see here, f prime is positive and f double prime is positive. Here, f prime is positive, but f double prime is negative. Here, f prime is negative and f double prime is positive. And here, f double prime is negative and also f prime is negative. I have given this kind of a thing as a test question before as well. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.